Assalamu alaikum students, welcome to my channel Physics with Hasnain. In this video, we are going to understand the physical meaning of Helmholtz free energy. We will derive its differential form, obtain its partial derivatives, and then use a simple thought experiment involving two identical systems to understand why Helmholtz free energy decreases when temperature increases. Let's begin. For a simple thermodynamic system, the first law can be written as where U is internal energy. This equation contains all thermodynamic information about the system. However, entropy is not always the most convenient variable to control experimentally. In many situations, temperature is fixed by the surroundings. Therefore, we would like a thermodynamic potential whose natural variable is temperature instead of entropy. This motivates the definition of Helmholtz free energy. We define Helmholtz free energy as where U is internal energy, T is temperature, and S is entropy. At this stage, the definition may look mysterious. Why do we subtract Ts from U? To answer this question, let us first derive its differential form. Taking differential of this equation gives df equals du minus t ds minus s dt. Using the differential form of internal energy, we obtain the t ds terms cancel and giving df equal minus s dt minus p dv. This is the fundamental differential equation for Helmholtz free energy. Notice that the differential form contains dt and dv. Therefore, the natural variables for Helmholtz free energy are temperature and volume. So we write f as a function of t and v. Now let us consider an isothermal process. Since temperature remains constant in this process, so we set dt equal to 0, and therefore in this condition we have df equal to only minus b dv. Suppose the process is reversible, the infinitesimal work done by the system is therefore df equal to minus dw. Integrating, we obtain this result is extremely important. It tells us that during a reversible isothermal process, the work obtained from the system is equal to the decrease in Helmholtz free energy. Notice carefully what this equation says. It is not the value of F itself that measures the work. Rather, it is the change in F that corresponds to the work obtained during the process. This is the first clue that Helmholtz free energy measures the part of system's energy that can be converted into useful work under isothermal condition. Now let us return to the differential form. From this equation we immediately obtain partial F by partial T at constant volume is equal to negative of the entropy of the system, and partial F by partial V at constant temperature is equal to negative pressure. The second relation is familiar, but the first relation contains a very deep physical message. Let us investigate it. Consider two identical systems. Initially, both are in equilibrium with a cold reservoir at temperature T low. Their volumes are fixed. Since the systems are identical, they initially have the same internal energy, entropy, and Helmholtz free energy. Now, we take one system and place it in contact with a hotter reservoir at temperature T high. The other system remains attached to the cold reservoir. Because the volume is fixed, the heated system does not perform any expansion work. It simply absorbs heat until its temperature becomes equal to T high. Now, let us ask an interesting question. Which system has the larger Helmholtz free energy? To answer this, we use the formula partial by partial T equal to negative of entropy. Since entropy is positive, so partial by partial T is negative. Therefore, increasing temperature at constant volume causes Helmholtz free energy to decrease. Consequently, the heated system possesses less Helmholtz free energy than the cold system. At this point, many students become confused. The hot system absorbed energy from the hot reservoir. Its internal energy increased. So why did its Helmholtz free energy decrease? Shouldn't more energy mean more ability to do work? The answer is that not all internal energy is equally useful. When heat enters the system, two things happen. Internal energy increases, but entropy also increases. As temperature rises, the quantity Ts grows significantly. In fact, Ts can increase faster than U. As a result, F decreases. This tells us that the part of added energy becomes associated with random microscopic motion. Although the total energy increases, a smaller fraction of that energy remains available for conversion into useful work during isothermal process. Now we can understand the meaning of Helmholtz free energy. The internal energy represents the total energy stored in the system. The term Ts represents energy associated with the entropy. The quantity represents the part of energy that remains available for conversion into work under isothermal conditions. This is why the work extracted during a reversible isothermal process is related to the decrease in Helmholtz free energy. The more Helmholtz free energy decreases, the more work can be obtained.